Bismillahirrahmanirrahim. Welcome in class of elementary number theory. My name is Azmat Ali and I hope you are all doing well. In today's lecture we will discuss division algorithm. So let us start from a simple example. Suppose we divide 9 by 2. This gives us 2 4s are 8 minus remainder is 1. This number is called divisor. This number is called dividend. This number is called remainder. And the last one, this is called quotient. Next, as you can write, 9 is equal to 2 into 4 plus 1. That is dividend is equal to divisor multiply quotient plus remainder. And this equation is simply called the division algorithm. Now, in today's lecture, we will prove the division algorithm in general for integers a and b. So, how can we state division algorithm? Statement. Let a, b are two integers belong to z with b is positive. Then there exist unique integers, unique integers q and r such that you can write a is equal to b times q plus remainder, where your remainder is 0 less than equal to r less than q. Your remainder lies between 0 and q. Sorry, this is b. So according to division algorithm, here a represent dividend, b is divisor, and q is quotient and r is remainder. You can verify it by a simple example. The value of quotient q and the remainder both are unique. This is not possible that you can find any other quotient when you divide 9 by 2. Can you say this? This is 9, so 2 5s are 10, remainder is minus 1. So these remainder and quotients are always unique. They are not different. So to prove division algorithm, I will divide the proof into three parts. We divide the proof into three parts. In part 1, we will show the form A is equal to BQ plus R exist. So first part is about the existence of this form. In the second part, we will show that this remainder r is always less than the divisor b. In the part 3, I will show the integer q and r are unique. So last part is the about the uniqueness of q and r. So to prove part 1, we will define here a non-negative set. So we begin by proving that the set I am defining a set as such that this consists on elements of the form a minus bx, such that x belong to z and a minus bx is greater than equal to 0. I have not defined this set arbitrarily. Uh, if we rearrange the expression a is equal to bq plus r to isolate the value of r, then we have r is equal to a minus bq. So this directly motivates us to form this set s is equal to a minus bx. Actually, the set s is equal to a minus bx. What does this expression show? This expression actually shows all the possible values of your remainder. So next we have to prove this set s is non-empty. To do this, it is sufficient to show is sufficient to show that uh, there exists a value of x that making this number a minus bx non-negative. Because in this set S, all of the number are greater than or equal to 0, so we will find a certain value of x that when we plug it, that value of x in this expression a minus bx, it should be greater than or equal to 0. Because the integer b, this is greater than or equal to 1. How this is greater than or equal to 1? Uh, if you see here, uh, our b is greater than 0, but it is an integer. In the set of integer z, the next integer to 0 is 1. So our b is always greater than or equal to 1 because b is positive here. So because the integer b is greater than or equal to 1, this implies if I multiply both sides of this expression by a absolute, we have a absolute into b is greater than or equal to a absolute. And so A minus B into minus A absolute. Actually, I will choose value of x is equal to minus A absolute. That will make this expression A minus bx greater than or equal to 0. So if we put here x is equal to minus A absolute, this gives us A minus B into minus A absolute. That is A plus B into A absolute. From this inequality, A absolute into B is greater than or equal to A absolute. So this is greater than or equal to A plus A absolute. Whatever your A, either it is negative or positive, this expression is always greater than or equal to 0. Suppose your A is negative, this is equal to, suppose this is minus 5. Then this number A plus A absolute, this is equal to minus 5 plus minus 5 absolute. This is minus 5 plus 5, which is equal to 0. And if suppose your A is positive 5, this is equal to A plus A absolute equal to 5 plus 5, which is equal to 10, that is greater than 0. So in any case, either your A is positive or negative, this number A plus A absolute is always greater than or equal to 0. And this shows A plus B into A absolute is greater than or equal to 0. So for x is equal to A absolute, x is equal to, sorry, minus A absolute, the number x is equal to A, the number A minus bx is greater than or equal to 0. This implies A minus bx belong to S. This shows S is non-empty. As S is a set of non-negative integers, so WOP guarantees that the set S has the least element Say this is R. So by the definition of set S, there exists a unique integer Q such that we can write R is equal to A minus BQ, where okay what is WOP stand for? WOP is well ordering principle. This principle says if we have any set of non-negative integers, like here S is a set of non-negative integers and this is a non-empty, then this well ordering principles guarantees that this set S must have the least element. So I say by this principle the least element is R. As the elements of set S, every element of this set S is an image uh, for given value of x. So if you say R is the least element of set S, it means there must exist an X for which R is the image. So I say this X is Q. So we can write R is equal to A minus BQ by plugging X is equal to Q here. So this completes the first part. The hence hence the form A is equal to BQ plus R, where R is greater than equal to 0 exists. Now we move towards part 2. In part 2, now we show that now we show that our remainder R is less than B. We suppose on the contrary, we suppose on the contrary that R is not less than B, it means our R is greater than or equal to B. Or we can say R minus B is greater than or equal to 0. But if we evaluate the value of R minus B, as my R is equal to A minus BQ, so by substituting the value of R, A minus BQ here, this can be written as by taking B common from these two terms, we have minus B into Q plus 1. This number A minus B into Q plus 1 is of the form is of the form A minus Bx, because x is an integer and q plus 1 is also an integer. So it is clear that this number R minus B belong to set S, because the set S having all the elements of the form A minus Bx, as the value of R minus B is A minus B times Q plus 1 is also of the form A minus Bx. This shows R minus B belong to set S. But R minus B is clearly less than R. This shows a contradiction, which is contradiction diction to the assumption that R is the least element. R is the least element because here R minus B is clearly less than R. So this shows R minus B is the least element. So this contradicts with our assumption that R is the least element. Hence, R is not greater than or equal to B. This shows R is less than B. Hence, the form A is equal to BQ plus R hold when our R is lies between 0 and B. Now we move towards the last part of the proof, part 3. existence of uniqueness of Q and R. Uniqueness of Q and R. We will prove this part also by contradiction. We suppose that A has a two representation. A has two representations. Otherwise, you can write it as suppose that there are uh, two values of Q, Q1 and Q2, and there are two remainders that opposite to the same value of A. So we suppose that A has the two representations of desired form. A is equal to BQ plus R, where R is lies between 0 and B. This is my first representation for A, and similarly I have another representation for A. A is equal to BQ plus 1 plus R1, and R lies between these two. As both are the representation of A, or by equating both values of A, we have BQ plus R is equal to B into Q1 plus R1. We can write this expression BQ minus B times Q1 is equal to R1 minus R by taking B common. We have Q minus Q1 R1 minus R. We do not know which quotient, either Q or Q1, is bigger. Similarly, which value of R is bigger. So for the safe side, we take absolute on both sides. This becomes Q minus Q1 is equal to absolute of R1 minus R. Say this is my third equation. Since our remainder lies between these, this shows if we find the difference of R and R1, R minus R1, R1 minus R absolute, this is also less than B. You can see this by an example. Suppose you say our R is less than suppose this is 5. Suppose this R is equal to 2. The next one is suppose value of R1 which is equal to 3. This is also less than 5. Clearly, when you find the difference of both value of R, this absolute difference is equal to 3 minus 2, the 3 minus 2, which is equal to 1, clearly less than the value of B. So here R1 minus R absolute is less than B. Combining with combining 4 and 3, combining 3 and 4, we have B into absolute Q minus Q1 is less than B. This implies Q minus Q1 absolute is less than 1. As Q and Q1 both are the integers whose difference is less than 1, this is possible that as the difference of two integers is again an integer, and this difference is less than 1. This is possible only when these difference is equal to 0, because 0 is the only number whose uh, which is less than 1. The, okay, this shows both q is equal to q1. 3 implies if you substitute these values of q in 3, what is the here? This becomes 0. This implies R1 minus R absolute is equal to 0. The As you know, if the absolute of some number is 0, this is possible if and only if the number is itself 0. This shows R1 minus R is equal to 0, and hence R1 is equal to R. Hence the integers Q and R are unique, and this completes the proof. So I hope now you have a clear understanding about division algorithm. Inshallah, in the next lecture we will discuss exercise questions related to the topic of section 2.1. So let us see in the next lecture. Take care. Allah Hafiz.